right, shall we begin? Welcome back. This is CS4510. L04B. The topic of today is regular grammars and closure. So pacing-wise, actually, we have like 6 lectures to do, and timing, it's like this was a lull because we need the full 2 hours next time. So but let's just talk about some kind of extra stuff in context-free grammars. We're going to prove today twice. Every regular language is context-free. A language is said to be a context-free language if there's a context-free grammar for that language. So we're going to prove that every language is context-free. First off, name every possible device that we know defines or accepts or decides a regular language. We have diaphase. We have anaphase. What else do we have? Regular expression. We also technically have G-anaphase. That was really just a useful thing in the proof of equivalence with regular expressions. We're going to take one of these and show that it's contained within LCFG. Which one should we do, though?
Regular expression.
Yes. This is the easy one.
It's almost grammar form already.
Yes, exactly. We'll actually do it twice. We'll do this proof, and then we'll do this one, just to show you the difference. So how is this proof going to work? Structural induction. Regular expressions, again, are defined by a kind of recursive definition. We're just going to show that the context-free grammars also satisfy such a definition. And recall last time we mentioned that regular language is the smallest class of languages with certain base cases closed under union, concatenation, and clean start. So we're simply going to do the same thing. So we proceed by structural induction. For L in our rex, there exists a regular expression, call it R, to describe L. Our base case is that R has no recursive rules. So R is equal to 4 options: the empty string, the empty set, A, and B, right? Give me a context-free grammar that produces the empty string. Yeah.
Produce just the empty string?
Yeah.
S to S empty string? Or even just empty string?
Yeah, simpler. Give me a context-free grammar that produces the empty set. Yes.
The empty set?
Not quite. We want this. This is a production, which means 1 non-terminal to 0 terminals and non-terminals. And it happens to be the case this only produces 1 string, which is the empty string. We want a context-free grammar to produce nothing, not even the empty string. It's like type addition. Yeah. That will not produce any strings. It's not the shortest. It's not the only one that produces the empty set. As in, it produces no strings. What about just A? Just B. Okay, 4 base cases, done. Each of the 4 base cases in a regular expression has a context-free grammar. Those are the 4 context-free grammars. Now, suppose that Ri, Rj are regular expressions with equivalent CFGs, GI and GJ. By equivalent, we mean that the language described by RI is equivalent to the language described by GI, and the language described by RJ is equivalent to the language described by GJ. Further, suppose GI, GJ have start non-terminals, SI and SJ, right? We give CFGs for what? L of GI union L of GJ, L of GI concatenated with L of GJ, and L of GI star. Okay, give me a context-free grammar for the union of two other context-free grammars. Yeah.
Would it be like S to L of S?
Not quite, not quite. So SI produces all of GI, and SJ produces all of GJ. Everything in L of GJ has to be following from a sequence of productions when you begin with SI, and so on for GJ, right? L of GJ. So what you do is you just non-deterministically guess which grammar you want to produce, and then do that. So add a new start. Now this is, you're supposed to write it all out, but I'm just going to tell you the answer. So everything I'm saying out loud is the answer. Just add a new start non-terminal S, and then have a production S goes to SI or SJ. Why does this new grammar produce the union? Well, if L is in L of GI, then there's production following SI. So the production in this grammar goes S to SI, goes there. And if L is in L of GJ, then it goes S to SJ to there. So you non-deterministically choose which one you start at, and then go from there. Okay? Now suppose, so the context-free grammars, in fact, are closed under union. Why is the concatenation of two context-free grammars context-free? Give me a similar construction. Yeah.
Y is equal to SI, SJ.
Y, let's do S.
S.
SI, SJ. Why does this work? That's going to be some word of SI. Following a production, this is going to bottom out. This is going to non-deterministically be some word in L of GI. This is also going to be non-deterministically some word in L of GJ. So they're going to be concatenated. Something in the before, something in the after. Done. Okay. Now what about star? This one's a little tough. Similar to when we did that the star of an NFA, we have to add the new start state and some other stuff. Something similar will have to happen here. It's going to be an edge case.
Do S go to SSI or empty string?
That's what I have. Actually, I don't remember if that is the bug or not, but I'm pretty sure that's right. That sounds right. So S is going to go to SI, which basically means you apply this production some number of times. This is going to produce SI, 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 and then, or none of those, right? Then each of those is going to perhaps be some word in the language of GI. So those are going to be concatenated. So this is 0 or more copies of the words of SI. So we've proven that each of these has a context-free grammar. So therefore, every regular expression has a context-free grammar. Done. Why is the containment not equal? Yes.
Because the grammar can produce strings that the rejects can't.
Like what?
Like, regex can produce an indeterminate amount of copies of itself.
I guess the answer I'm looking for is like, by the pumping lemma, we prove some languages we prove the regular expressions are equivalent to NFAs and DFAs and so on. And we prove there's no DFAs for certain languages. And those would be A to the N, B to the N, and WWR and so on, right? But we gave a context-free grammar for A to the N, B to the N. So just by set theory, we know that A to the N, B to the N is in here, and then not in here. Therefore, they're not equal. So we have proven now that every regular language is context-free. That means the relationship is not something weird like this, but rather like that. So we know that this is the case. Questions on that proof? All right, what if we do it a second time? Let's prove that every DFA has, we won't prove, actually, we're not going to prove that every DFA has a context-free grammar. We'll prove something else. Every DFA is equivalent to something called a regular grammar, okay? So let's define a second kind of grammar. While a CFG has the property that the productions look like this, a single non-terminal goes to an arbitrary string of terminals and non-terminals. The right-hand side is totally relaxed. We will instead define a regular grammar to be as follows. A single non-terminal can either go to a single terminal followed by a single non-terminal, or a single non-terminal, or the empty string. That's the only thing allowed. In practice, what this means is the first one you have A can go to B, C, D, E, F, G, H. Regular grammars only look like A goes to B, C, or D, or empty string. Something like this. So we restrict the rules significantly. You cannot have an arbitrary number of long right-hand rules. And furthermore, the terminal must come before the non-terminal. You can't interchange it or anything like this. So it has to look exactly like that. Now, these are called regular grammars. Everything else is the same, V, sigma, S, P, whatever, right? I claim that the regular grammars are equivalent to the regular languages. Not only, I mean, obviously they're called regular grammars, so you should expect that. Like same with regular expressions. But why is it true for free that this implies that every regular language is also context-free? Yes?
Can you restate the question?
Yeah, sorry. We are going to prove that the DFAs are equivalent in power to the regular grammars. Why does that immediately imply for us that every regular language is context-free? Assuming we didn't just do this proof, but that showed that. Why do we get that for free if we can show that? Trivially, every regular grammar is a context-free grammar. Right? Same way every DFA is an NFA. If you have a grammar that looks like a regular grammar, it's also the definition of a context-free grammar. So you're good, right? Context-free grammar is simply generalization. So this part you get for free. So by showing that these are equivalent and then this is contained, you get every DFA has a CFG for free. So here's how it's going to work. Let L be an element of L DFA. Then there exists a DFA, a D, which is, what is it, Q, sigma, Q0, delta, and F. We give CFG a G, which is V, sigma, the productions, and S, such that L is which is decided by this grammar is equivalent to the one being decided by this DFA, which is equivalent to this L. discovery, not a CFG specifically, a regular grammar. Right? It's fairly simple, actually. So let's give the parts. V is going to be equal to a set of terminals and non-terminals. It's going to be equal to a set of non-terminals. The proof actually, okay, so to prove that every DFA can be equivalent to a regular grammar is actually a very tedious proof. It requires 4 parts. First, you show every DFA can be converted to a regular grammar, and then you do an if and only if. Then you can convert every regular grammar to a DFA, and then you do another if and only if. So technically 4 proofs that almost look identical. So instead, we're just going to prove this way, because the construction will be kind of obvious. And to do all 4 parts may have a little bit of edge cases that we don't really care. What we're just going to show is that a regular grammar basically simulates a DFA. What we're going to do then is have states Q0. For states Q0 to QK, we'll make our non-terminals that. So for every state of the DFA, add a non-terminal to our regular grammar. Sigma is, you're not going to believe this, just sigma. Now the productions are going to be as follows. If we have in our transition function QIA equals QJ, that is, some state QI on an A, perhaps any symbol goes to QJ, what we're going to do is add what kind of production? See if we get this. I don't think we should.
First kind?
This kind, yes.
Yes, that kind.
What should the production be? For this specific QI, A, and QJ, let's say.
UI goes to AQJ.
That's basically like the entire simulation, right? As the DFA goes A, B, B, A from a sequence of states, this is going to go to QI, it's going to print the A in the front of it, and then QJ will print some B, which will print an A, which will print an A. That's basically the whole simulation right there, right? We have a little more baggage though. For QF is a final state, add a production of the form QF goes to the empty string. We need to accept somehow. And then what's our start state? Q0 is obviously the start on terminal, right? Now let's just give a high level idea about why this works. So suppose that the DFA accepts a string. It goes from state to state to state to state to state. The regular grammar also goes through those exact sequence of states following these kinds of productions. Then let's say the DFA accepts the word. If it accepts the word, it stops right there. This production in this regular grammar is going to replace that QF with a empty string. So it'll just be left with all the sequence of symbols before, concatenated, and then there. And because there's no more non-terminals, the grammar produces the string when the DFA accepts. High level idea. The other argument, why, if the DFA rejects a string, does the grammar not produce the string? Well, notice that every single kind of production is 2 kinds. One, it either keeps the number of non-terminals the same or it decreases it. So in fact, through any of the working strings, there's never more than 2 non-terminals. There's never more than 1 non-terminal. There's not 2. You go 1 non-terminal to 1 non-terminal, or 1 non-terminal to 0 non-terminals, right? So you're going to go 1 to 1. So every time you apply a production, in fact, and in fact, this is not even a non-deterministic grammar, really. There's exactly, in the sense that, given a working string, there's exactly 1 non-terminal left to produce. Now, which transition you take, if it was an NFA, for example, then that would be something you would do. But there's exactly 1 non-terminal you choose to produce. Unlike when we did like S goes to SAS, BS. In the working string, you could choose either of those to expand upon as your next decision. Here, it's going to go Q0 to AQ1, and your working string is going to have exactly Q1 there. So you're only going to have 1 non-terminal. Next thing is, you can only have 0 non-terminals if you land in a final state. If the DFA lands in a final state, then you can get rid of the non-terminal, the one non-terminal. But if you don't land in a final state, you can never get rid of it. So a computation towards a reject state is not going to be able to get rid of the non-terminal in the working string, so it's going to have to not produce that string at all. So therefore, this is an example of grammar, a regular grammar, in fact, that produces exactly and only the strings that a specific DFA would accept. Kind of the argument there. Now that should be 4 proofs of induction. But let's just save some time and just say, obviously, we can edge case that out and we can do that 4 times, right? QED. Questions on that, on the regular grammar? Yes?
When do we use the second product, the one that turns into an, yeah, that one?
If I were to do the proof for an NFA, that would be an epsilon transition.
I see.
Yes. If we had QI, QJ, that's just QI, QJ, right?
That's what I figured.
Yeah. I wanted to do it, so when you do proofs on regular devices, and this is true general advice, you have many things to choose from, the DFA, the NFA, the regular expression. And the NFA is great because it's general, but sometimes you want something specific, so you can say certain things. For example, the pumping lemma was done with the DFA. We were specific about the DFA, because the determinism helped us get that loop thing. Sometimes you want a structural induction, so you look towards regular expressions. So there are pros and cons to all of them, and you choose the one that works the best. It's going to be sometimes it's the DFA because you want the determinism, sometimes it's the NFA because you want the generality, and sometimes it's the regular expression if you want recursiveness. Questions on this construction of the regular grammar? Okay. Let's talk about closure. So we all recall at a 2050 level what the term closure means. Does anyone not remember closure? So closure is basically given an operation in a set. Applying that operation remains you in the set. For example, the naturals are going to be closed under what? Addition and multiplication, but not subtraction and not division, right? So what this means is that, for example, if A comma B are naturals, then that implies that A plus B is a natural. That's what we mean for a set to be closed under an operation. So it's closed under an operation is if you take 2 elements in the set, you apply the operation, you're still in the set. It's not closed under subtraction because the difference of 2 natural numbers could be negative, and the smallest natural number is 0. 3 minus 7 is less than 0, right? Not a natural. Division, 2/3 is not a natural. But 2 and 3 are naturals. So you can apply the operation and get out of the set. So it's not closed under these, but it is closed under these, right? Let's talk about closure of the things we know. LDFA is closed under what? Let's just go through the list real quick. And when I say LDFA, I don't mean DFA specifically. This is equivalent to LNFA, L regular expression. Set theory, these are, instead of numbers where you add and subtract and stuff, these are sets, so you can do things to sets. Let's just quickly review. Why are the regular languages closed under union? There's 4 reasons, actually.
By definition of the regular expression?
Yeah, so regular expressions, that's one reason. The regular expressions take the union of other regular expressions, so by the inductive proof we did, the structural induction. What's another reason?
You can like merge the start states of the DFAs and NFAs?
Yeah, you could do that NFA trick that we did, right?
Yeah.
Which was actually the proof in the regular expression equivalent to NFA. Yeah?
The DFA can only transition to known states.
But why are the regular languages closed under union? Let's do the DFA definition, actually. Why is the DFAs, if I give you two DFAs, how can you give me a DFA that computes the union of the 2 DFAs?
With an epsilon transition?
That would be an NFA? That would be, in fact, the easier way. This is not an analytical question, this is a trivia question, actually. We technically did it in class.
You need the final state, the F state.
Not quite, because that could require non-determinism. Answer I'm looking for, we already forgot, is the Cartesian product of DFAs. You take two DFAs, you multiply, and you get that big thing, you know, combine all possible states, and then, what was it, you set the final states to be like Q1, it was like Q1 times F2 union F1 times Q2, right? You select, you do a DFA to simulate two DFAs at the same time, and then accept if either of them accepts. Many reasons the DFAs are closed under union, right? Intersection. Okay. Given the definition of the DFA, why are the DFAs closed under union? Excuse me, intersection. Same reason? DFAs, we did the product. So given two DFAs, Cartesian product them, except only if both accept. Right? We recall that. Given regular expressions, how do you take the intersection of regular expressions? It's a trick question. You can't. How would you, the only way to do it is, in fact, you can't, given non-determinism, you can't do ands and complements really easily. You can do unions and ors really easily, though. You can guess if there is an answer, but you can't say for every. It can do existential stuff, but not universal stuff, right? So, okay, yeah. So the only way to take the intersection of regular expressions or NFAs would be to convert them to DFAs, perhaps with a large blow-up, exponential, right? Actually, you convert the regular expression to an NFA, then you convert the NFA to a DFA using the exponential blow-up, and then you take the Cartesian product of those two, and then you could perhaps convert back. That gives you something really ugly and messy. So it's not really possible, it's only possible on technicality. Okay. Complement. Why are the regular languages closed under complement? That is, if I have a set of strings accepted by a DFA, the complement of that set, the opposite strings, are accepted by a different DFA. Or NFA, or regular expression or something.
Flip the accepting states.
Of what?
The DFA?
Yes, the DFA. The DFA says yes and no with equal power. So if it accepts, the things that land on the non-accepting states reject. So just Control F, return true with return false. So everything that's supposed to be rejecting should now be accepting, everything that's supposed to be accepting is now rejecting, right? So they're closed under complement because you can do that, take the complement of the states of the DFA. Now you can't take the complement of the states of the NFA. There's no complement operation with a regular expression, or even regular grammar, right? Concatenation. Why are the regular languages closed under concatenation? Which is that if L1, L2 are regular, then so is L1 concatenated with L2. Yes?
Because they're just side by side, they're not really.
We did it
Yeah.
when we proved the regular expressions. Closed under concatenation. We took the NFAs, right? We did it like that. What else we got? We got a star, clean star. Why are the regular languages closed under clean star?
It's just repetitions.
Yeah, we did it. We also did it with regular expressions. okay? Here's one, what about the difference? The difference of two regular languages is regular. What does this mean? If L1, L2 are regular, then so is L1 subtract L2. Now what is set difference, what is the definition of set difference? A minus B is equal to X is in A and X is not in B. So pictorially, the difference is you take everything in A and you remove things that were in B, right? That's the definition of set difference. Why are the regular languages closed under set difference? Yes?
You can only obtain end states that were in the original, that were in A, and A is closed.
Yeah, so let L1 and L2 be regular. So they have DFAs, let's say, or regular expressions or NFAs or something. They have some one of those devices. Why is the difference regular? You were starting on the right path, I think.
Because it's just a subset of this.
But subsets of regular languages may not be regular. Consider the fact, this gets everyone every semester, and it got me the first time. A to the n, B to the n is non-regular. But it is in fact a subset of A star B star, which is regular, because that's just a regular expression. And in fact, every language is a subset of sigma star, because sigma star is so general, it's just like every string, but everything is a string, so it's a subset of sigma star. And even the other way, this contains a regular language, which is the empty set. Right? Yes?
Can we construct that with all that?
Sure, how? Describe to me how.
We invert B, and then we intersect A with the inversion.
That's the definition of this difference of two languages. Here's kind of the proof I wanted to write it out a little bit more. We give a DFA, so you can apply closure to prove a language is regular or not quickly without having to construct any DFAs, NFAs, regular expressions, GNFAs, or regular grammars. Just throw closure at it. Recall how we proved the Dick language was not regular. We took its intersection. It's closure. You can just throw things around without having to actually build it. Let L1, here's what I would say, let L1 and L2 be regular. Therefore, L2 complement is regular by closure. Therefore, L1 intersect L2 complement is also regular by closure. The intersection of regular languages is regular, and the complement of regular languages is regular. Done. Now, suppose I wanted to do it the hard way and make a DFA for it. Here's what I would do. Make a DFA for L2, complement the states, make a DFA for L1, complement the DFA for L1, Cartesian product the DFA for L1 with the complemented DFA for L2. Now that's a harder and worse construction. We don't have to do any of that. We can just kind of throw closure at it and implicitly it works for us. Okay, homomorphism. Here's a hard one. Has anyone heard the word homomorphism? Okay, you may have seen homomorphisms but not known that they're called that. A homomorphism has a very nice property. It's a function that looks like, it goes from sigma star to sigma star, such that like h of, let's say, I don't know, a1 to ak is equal to the concatenations. a1 to ak is a concatenations of symbols, it's a word. But the homomorphism of a string is equal to the concatenation of the homomorphism of the letters. So in some sense, a homomorphism is a very pleasant looking function because it has a nice osmosis property. Homomorphisms are more interesting in like a multiplication sense. Here the implicit operation that's not listed is not multiplication, but it's a concatenation, right? What it basically means is you can do the concatenation before or after, right? So you could do, let's say before you take the map, let's say we want h of AB is equal to h of A, h of B, right? You go, A is here and B is here, then you can concatenate them to be h of B. to be AB, excuse me. Then you map A to H of A. You can map B to H of B. And then you can, if you concatenate them after, you're promised to get H of AB, which is what would have happened if you mapped the element AB itself. So you can either do the concatenation before and then take the map, or you can do the concatenation after, you can take the map and then do the concatenation. That's not true of every function. Not every function is homomorphism. But homomorphism is very aesthetic because it kind of looks osmosis-y, right? This is a pretty equation in my opinion. There are all kinds of other homomorphisms in like math, but this is a homomorphism from strings to strings, right? Suppose we have a homomorphism. What, for any homomorphism, is the empty string? If it's a homomorphism, every homomorphism has the same homomorphism for the empty string. Yes?
If I understood you correctly, the empty string is the same every time.
Basically. Why? Consider like H of A is just H of A, right? But A is also A concatenated with the empty string. So then H of A empty string is equal to H of A, H of empty string. But then we know this is also just equal to H of A. The only way that works out is if this is the empty string. It's an identity. It's like a multiplicative one, you know. So that's one property of the homomorphism. Second property of the homomorphism is that the only thing that really matters for the homomorphism is the map of the symbol A and the map of the symbol B. Because you break the word down into its letters, and then you map each of the letters. Really all that matters, and assume sigma is AB here, that these are these two things. So for example, let's suppose A went to BA, and then B went to ABB, right? Let's suppose our homomorphism can be defined just by these two strings. What is then H of A, let's say BBA?
Like the actual output.
Yeah. What is this specific map? What does that map to?
ABB, ABB, BA.
Yes, correct. So you can take strings and map them to other strings via homomorphism. Let the homomorphism of the language be the homomorphism of each string in the language. So H of L is, you take each W and L and you map it to the homomorphism. So while L contains BBA, H of L is going to contain ABB, ABB, BA, right? Here's my claim. For H any homomorphism, L regular, that implies H of L is regular. Why? Let's think about it. I claim that the regular languages are closed under homomorphism. That is, if you take the homomorphism of a regular language, as in the set of strings of each string applied the homomorphism to, I claim that H of L is regular. Two proofs of this, in fact. See if we can find either. Yeah.
So the concatenation of the regular language is a regular language.
Yes.
So H of a regular language can also be concatenated.
You're almost there. There is a intermediary step. That's pretty, I see. So like if we were to do a proof by induction, actually, I think that's a third proof. You would induct upon the symbols. Because this is something produced by one of our regular devices. The next one would be produced, concatenation of each string. But the concatenation of languages is regular, but yes, but you don't get to control which strings are concatenated with which. So I think the argument would work, but it would be very difficult. So that actually would work. There's a third solution. Let's find two easier solutions. Again, to prove something is regular, by the way, if I say prove this is regular, just give a DFA, NFA, regular expression, regular grammar, GNFA for it, or apply closure. You're not gonna be able to apply closure here. So pick one of the 5 devices. You don't need all 5. Pick one of the 3, DFAs, NFAs, regular expressions, and we go from there.
Perhaps regular expression is easier.
Okay, that's one proof. Why?
Because every literal, right, could be just replaced.
QED. Just structural, and you can do a structural induction. If you have, let's say, a regular expression with, let's say, A, B, union, A, B, B, star, all you do is replace every instance of A with H of A and every instance of B with H of B. That technically works. The proof is by a structural induction, though. So that's one solution. I think it's less obvious than the second solution. Suppose we did it with a DFA, or even an NFA. If the DFA has transitions like QI, read an A, QJ, while the DFA takes a sequence of transitions and it prints that out or accepts it, right? A, B, B, it doesn't print it out. That's the sequence of strings, it's symbols in the string it accepts. We want, when A, B, B to be accepted by the DFA, we want to make a second DFA that would accept H of A. So what we do is we copy the states over and everything, and then we do a little trick. So while this would take an A transition, we want to take an H of A transition. That's kind of the idea. Just inject a sequence of little states there, because, or use the GNFA definition, but just allow yourself to put a string of 0 or more symbols on a transition instead. Just a long chain. Now, when this DFA would take an A, this DFA is going to take an H of A. So then when this takes concatenations of symbols, this is going to take concatenations of the map of those symbols. Done. Yes?
Does one-to-one mapping, is that true for homomorphism?
They could be erasive, in fact. They could be like H of A could be like the empty string. Things like that could be possible. All kinds of ugly stuff. The only property that you have homomorphism is this aesthetic splitting property and no other assumption. Because other things, yeah. Every string must be mapped though, but not every string would be accepted. Questions?
Would that be technically an FA because you have no way of guarding whether, you have, for example, 2 A's or...
Exactly, yeah.
And you need the implicit reject, I feel like.
Yes, you do, yes. So it'll be the NFA definition, yeah. Okay, questions on this one? Okay. Reversal. If, what I claim is if L is a language, define the reversal of L to be the reversal of each of its strings. Right? So if your language is like A to the N, B to the N, the reversal of that will be B to the N, A to the N. The language of even length palindromes, its reversal happens to be itself, actually. So that one's kind of, and any of its subsets, in fact, are equal to itself. I claim the regular languages are closed into reversal. Why is the reversal of a regular language regular? And again, the theme of all these proofs is that there's a lot of little details we could be working out. We're not going to. We're not going to do any complex proofs by inductions or anything for these. We're going to kind of like outline the general thing. Because really, it's the same intuition you have when you program. You're making a structure, right? if L is regular, why is the reversal of L regular? Yeah?
Can I just reverse the NFA?
Yes, but a little more, we do need one more detailed thing.
The start state? Something,
Reverse the direction you're reading from?
Yeah, I mean, I think you guys got it. Like, so if, in the NFA, take the NFA, and if you have QI goes to, on an A goes to QJ, what you're gonna do is on the reversal, you're just gonna, the path, an NFA accepts a string if it's a path that takes you to the accept state. So just go backwards. Well, that's not the only problem. Okay, an NFA, first problem. NFA can have multiple accept states. How do you fix it?
you create a new star and epsilon into the original accept states.
Yeah. So let's just do it like this. Suppose this was our old NFA. Okay? We're going to make a reversal NFA as follows. First, we epsilon to a new final state. Okay? I'm going to draw this in an animated fashion. Okay? We're going to epsilon to a new final state. Then we're going to reverse every single transition. Right? We're going to make the single new final state now a start state. And the old start state is going to become the new accept state. Done. Without much further detail, do you believe that you could reverse the paths in the DFA, in the NFA, excuse me, a little bit of baggage on the edge cases here, but that'll give you the reversal of the language. By the fact that we've constructed a NFA for the reversal must be regular, QED. If there's a path from here to here, there's a path from here to here, and so on. Right. Questions on that one? Yeah.
So is that basically saying that because we can take an NFA and reverse it, and an NFA is regular, then the reversal
Exactly.
is also regular?
Exactly. Let L be regular, then there exists an NFA for it. We give an NFA for the reversal. That's how it usually says. When you get the assumption that L is regular, you get a lot. You get there is a DFA or an NFA or anything for it. You get to use that, chop it up, recombine it, spit on it, do anything you want to it. All right, that's all I have for the regular languages. Let's do context-free languages real quick. Okay. CFGs. Oh, we'll say CFLs, context-free languages. Why are they closed under union?
Can you just union the starting grammar?
Yeah, we proved it, right?
Yeah.
Concatenation. We also proved it. Star. We also proved it. Okay. Intersection. Are context-free grammars closed under intersection? Surprising. You can build a DFA for the opposite of of one DFA can simulate the opposite of another. You cannot make a context-free grammar for the opposite of another context-free grammar. You cannot take two context-free grammars and them together, it turns out. Here's the proof. Consider L1 is equal to A to the N, B to the N, C to the M. N comma M are natural numbers. Call that L1. L2 is going to be A to the M, B to the N, C to the N, N comma M are natural numbers. Why is L1 context-free? Give me a grammar for L1. S is going to go to XY. X is going to go to AX, B, or epsilon, and then Y is going to go to C, Y, or epsilon, right? A's and B's match any number of C's. Similarly, S is going to go to, for this bottom one, let's call it UV, just be different. And then U is going to go to A, U, or the empty string. And then V is going to go to, I should not have used V, but it's fine. B, V, C, or empty string, right? So both those are context-free. So L1 and L2 are context-free. What does L1 intersect L2? Yes?
Is it the empty set?
No, because there are, certainly the empty string is in both. But there's more strings in both, I claim.
A, N, B, and C, N.
So, number of A's equals the number of B's, if it's an L1, and if it's an L2, number of B's equals number of C's. So number of A's equals B's equals C's. So this is A to the N, B to the N, C to the N. That's not a language you've seen before, but we can't prove it yet. We'll prove a pumping lemma for context-free languages. Later, I'll prove to you that this is not a context-free language. There is no context-free grammar for this. Why that's true, there is no intuition we have about it right now. The context-free grammar can like pair things up, but it can't like triple pair things up. Exactly. So intuitive, there may not be good intuition yet about why this doesn't work, but it doesn't. I promise you it doesn't. There's no context-free grammar for it. We'll be able to pump the grammar. Okay? So they're not closed under intersection. That's the difference between regular grammars, regular languages, in fact, because regular languages are closed under intersection. This generalization of the regular languages is not closed under intersection. Surprising. Complement. Are they closed under complement? Is the complement of a context-free grammar context-free?
No.
Yes. I mean, correct.
By closure? Because I want to say no by closure, because if you could do the complement, then intersection would also be possible.
Exactly. Assume to the contrary. They were closed under complement. Then for L1, L2 CFLs, so would L1 complement union L2 complement, which is what?
L1 intersects L2.
Contradiction. If they were closed under complement, since they're already closed under union, you would get intersection for free. But you don't get intersection. We didn't finish the proof because we haven't shown this to be not context-free, but assume we did. Then since they're not closed under intersection, they also cannot be closed under complement. Okay? No, not closed under complement. Difference. Wish I could spell. Are they closed under difference?
No,
Why not?
because they're not closed under complement.
Yes, but how would we prove it? That's exactly the idea. We're gonna, complement relies on intersection, difference relies on complement. But why? Assume to the contrary, they are, then for L, a CFL, so would be what language?
CFG or
We want to reach a contradiction. I'll just tell you. Sigma star minus L is what?
complement of L.
Yeah. Contradiction. So if they were closed under difference, you could get complement for free by subtracting L from everything, that would give you the complement. And if you got complement, if you got intersection, you don't get complement because you don't have intersection, and you don't get difference because you don't have complement. Right. So they're not closed under anything that isn't just a nice union. They're closed under union and all the other like regular expression stuff, but like nothing else. This is kind of why regular expressions don't have complement. They're not defined to have a complement. They have those three operations, that's it. You can't add in any other operations. Okay? Let's just keep everything up here about homomorphisms. I claim the context-free languages are closed under homomorphism. Why is the homomorphism of a context-free language context-free? And again, homomorphism, same thing. H of L, but instead of H of L having a DFA or regular expression this time, suppose H of L has a grammar. Why is the context-free languages closed under homomorphism? Yes.
Because the CFG is closed under homomorphism?
Yes. So every proof we're going to modify the CFG. Tell me how to modify the CFG.
Replace the terminals.
QED. Suppose, for example, S goes to ASB or empty string, and let's suppose H of A was BB, and H of B was AAB. All we're going to do is have S go to H of A, S, H of B, or in the empty string, which is really going to be S goes to BB, S, AAB, or empty string. You do the surgery on the grammar itself. Certainly, if that was going to produce an A, the same sequence of productions will produce the BB. Right? So if a word is produced by this grammar, its homomorphic image will be produced by this one. Close under homomorphism. Reversal. Why is the reversal of context-free grammars context-free? Again, proof intricate little details. Let's do the high-level idea. Just the surgery on the grammar. We have one grammar that produces something. Give me another grammar that produces the reversal of that. Yes?
If you were to swap the rules,
How so?
so if like S is equal to PSA, you would simply switch it.
Reverse it, yeah.
Reverse it.
So let's say S is equal, goes to U1, U2, to UK for these. Just reverse every rule. Done. So the context-free grammars are closed under reversal. Proving things like this, you take the object itself and then you do surgery on it and you show that it accepts or produces the modification of the strings, whatever those are supposed to be. Questions? All right.